Okay, welcome back. This is going to be the last video in this set of videos on material selection and introduction to Ashby charts. This is, again, Dr. Matthew J. Traum. You've gone through the last three videos, and we've gotten all the way to the end of this example on how to select the lightest material that can withstand a given force for a material that's basically just a member that's in tension, that has a cross-sectional area that we can adjust but a length that we can't. So we've talked about how to derive the value index, how to screen and apply the attributes that come from the customer to eliminate possible choices. We've talked about how to rank order and evaluate using the charts, the various indices to pick some candidate materials. And then the final step is what I call the deep dive into documentation. And there's really nothing to say here other than the list of materials that we came up with here for step number 3 in terms of the ranking. These are all candidate materials, but other than being selected because they have this high C ratio, we don't know anything else about them. And so this is the point where once you have your short list of maybe 5 or 6 materials, you go into the customer needs and go into the standards and start identifying additional attributes that would make those shortlisted selected materials either more favorable or less favorable. So things like cost and manufacturability might be of interest, right? So we probably would throw out diamond, right? Because diamond is pretty darn expensive, and you wouldn't want to just be making kind of run-of-the-mill components out of diamond. That would be a very, very specific and specialized application. And carbon reinforced polymers have some special manufacturing constraints associated with them. They have to be made in a very particular way. So you might not actually be able to make this part using CFRP, and so you might choose to throw out CFRP because of manufacturing concerns. Another one is material compatibility. So things like putting multiple dissimilar metals into the same assembly could give you some pretty serious corrosion problems. And so you might not be able to choose aluminum or magnesium because you might have steel or something else as your other components, and you could create a situation where you're exacerbating the formation of rust and causing things to fail that way because they rust more quickly than you would otherwise expect. And of course, there's a whole bunch of other ones that I won't list here because they're basically determined by your specific application and what your customer is telling you their needs are for the specific part. But ultimately, once you have your short list, then you can do a documentation deep dive and get more information about all of these sort of secondary attributes, and ultimately picked from your short list the best material that has the highest value of C, but also satisfies all of these kind of secondary concerns that weren't part of the initial analysis. Okay, so that ultimately wraps up the material selection procedure number 2, or use number 2 for an Ashby plot, which shows you how to do that material selection. And so we're now in the home stretch here. We're on the last topic, which is just me wanting to show you guys some alternative Ashby plots. So here's one which has the strength versus the relative cost. So whereas before we were talking about diamond being awfully expensive, if you look here on the x-axis, we've got relative cost. Again, all of these Ashby plots are all logarithmic on both scales. So each one of these ticks represents an order of magnitude increase in the cost per unit volume. But way over here, we've got the tungsten alloys, which are quite expensive in terms of metals. But then if we look all the way back over here, The least expensive metals would be things like aluminum alloys, and then even cheaper are carbon steels and cast iron. So this gives you a whole range of the costs associated with all of these different materials. So that's one kind of neat Ashby plot that has a very slightly different type of axis, which is kind of a cost instead of a material property. And then you guys know that I'm a thermal fluid sciences guy, and so I couldn't go a whole presentation without giving you at least one kind of thermal fluids type plot. So here is a plot of thermal expansion on the y-axis versus thermal conductivity on the x-axis. And here you see this really sort of neat trend that's kind of universal to all materials, which is the idea that if you have high thermal expansion, you have relatively low thermal conductivity. So there's this very clear trend. High thermal expansion, low thermal conductivity. Yep, you have this very clear trend that kind of runs from left to right in this direction across this plot. So if you wanted to do something like calculate the value of electrical insulation that you were using versus some heat transfer process, or you were worried about how well some thermal insulation performs in an application, this is a plot that you would use for those sort of heat transfer like problems. So the Ashby plots, the Ashby diagrams extend beyond just material properties to a lot of other physical properties for materials that can be useful for other types of questions beyond just sort of mech design, mechanics of materials type problems. Okay, so that brings us to the end of this presentation. Appreciate your time and look forward to seeing you in class. Thanks. See you soon.